Okay, we're going to be going over homework 2, part B, or part 1, and part A. Using energy balance, we're going to derive an iterative algebraic expression for calculating thermal diffusion through a uniform bar, assuming constant thermal diffusivity via explicit differencing of the temperature gradient. So, in order to do this, we set up a diagram here of our bar of which our heat is diffusing through. We set it up into slabs in order to kind of calculate our temperature gradient that we're going to be calculating, and so let's just go through and start labeling this out. We have a cross-sectional area right here that is going to be constant all the way through this bar, so that'll be our A. And then we also going to have a constant thermal diffusivity, and we're also going to have a constant difference in these slabs on how wide they are from the last one to the next one. Okay, and we're going to be labeling these as TJ as for one of these slabs for the middle slab, and then we're going to have TJ plus 1 and TJ minus 1, since this one and this one are going to have influences on what this TJ is going to be, since we're going to have a heat coming in from here, and we're going to have heat coming in from this side also. So both these are going to have an impact on TJ. Next thing that we can do is we can go over the first part of our energy balance, which is going to be our accumulation term, which is going to be dt, or partial derivative of temperature, over a partial derivative of time. And we'll go over this later, but for right now, our goal here is to get joules per second on this side for our units. And in order to do this, we're going to have this partial derivative right here. We're going to multiply it by our heat capacity, and this is going to give us joules over grams times Kelvin or Celsius, whatever we're using, and then times our temperature unit over seconds. Okay, so we can cancel out our temperature unit, and we're going to be left with joules over gram seconds. And so we have to cancel out the grams. That will be our main goal here. So in order to do that, we're going to use our density, right? So we're going to use our density, and we know that density times volume gives us our or gives us grams, or mass. So we can plug this in here. We'll have our rho times our V times our C over our partial derivative of T over our partial derivative of time, or temperature over time. And we can then solve for this volume unit. So we know that our cross-sectional area is constant all the way throughout this bar. So we can calculate the volume of the slabs by using the constant difference in lengths of these slabs, and those two together will give us our volume. So our new equation will look like our rho, and then we're going to have our A times our heat capacity and we're going to have our partial derivative of temperature and our partial derivative of time. And this is going to be equal to our heat flux Q, which is going to be our in minus out factor right here in our energy balance. But we know something called Fourier's law, which equals Q, which we will plug in. So Fourier's law is going to be Q is equal to negative K times our cross-sectional area, our partial derivative of T, and derivative of our X, which we can simplify down to is negative K, A, and then this is going to be our TJ plus 1, that's our first temperature, minus our TJ over delta X, because that's our change in distance for our slabs, and it's constant. So, and then we're going to have plus, because we also have a diffusivity happening from the other side of the bar, so we have to include that too. So that's going to be TJ minus 1 minus Tj over delta x. And then we can combine these. So it's going to be negative Ka, and we're going to have Tj plus 1 minus 2Tj plus Tj minus 1 over delta x. And we can do this because we have a like denominator at the bottom here. So we can go ahead and plug this back in for Q down here. We have rho A, C is equal to our negative Ka, Tj plus 1 minus 2Tj and plus Tj minus 1 over delta x. And what sticks out here, we have an A on both sides of our equation, so we go ahead and cancel those out, and we're left with our rho C T over our partial derivative of T is equal to negative K Tj plus 1 minus 2Tj plus Tj minus 1. Over delta x. Okay, so we can now look at our thermal diffusivity constant, and we can look at the units here. So the units for diffusivity are going to equal K over PC, or rho C. And oh, I forgot right here, when we sub for our volume, I forgot to include our delta x, because our delta x times our cross-section area, like I said, is going to give us our volume. So we need our delta x here, and then our rho. And the a's still cancel. So, but anyway, so we have K over PC here, right? So we can divide this K over to this side of the equation, and we're going to have our rho C over K. So it's just going to be the inverse of our diffusivity right here. So we can go ahead and plug this in. So we're going to have our delta x over our diffusivity, and then we're going to have our partial derivative, and then we're going to have Tj plus 1 minus 2Tj plus Tj minus 1 over our delta x. Okay, so the next thing that we need to look at is our goal here is to find our steady state through this equation, and in order to do that we have to look at this derivative, and we're going to have to kind of expand it out. So for this derivative right here, we have our temperature over a time. So our temperatures are going to be, let me move it over here. So we're going to have our dt over, or our partial derivative t, or temperature over our partial derivative time is going to be equal t, and then our j, because that's what we want to find. And we're going to have our n plus 1, which is going to be our n time of our derivative. And that's going to be kind of our goal, what to find here is going to be our n temperature at the n time that we set. And then this is going to be minus, because it's a derivative, so it's going to be the difference. It's going to be minus by our original time of Tn. And this is going to be over a delta T, our temperature, or our time constraint that we set. So we can go ahead and plug this in here. So we're going to have our delta x over our diffusivity, and then we're going to have our T n plus 1 j minus our T n j over our delta T. That's going to be equal to our T j plus 1 minus 2 T j plus our T j minus 1 over our delta x. And like I said before, this is going to be, this is going to be our end goal right here, is to find this Tj n plus 1. We want to find what this final temperature is after it reaches a steady state. So we're going to want to separate this out and get it on the left side by itself. So we'll go ahead and do that. So we'll have our, basically just want to move this over here, and then we're going to just multiply it over. So we'll have our delta t of diffusivity on top over here, and this is what's in our tj n plus 1 minus tj n, what's going to be left once we do this. So we're going to have diffusivity delta t over delta x multiplied by our tj plus 1 minus 2 tj plus tj minus 1 over our delta x. And then we can go ahead and add our tjn over to the other side, and we're going to be left with our tjn plus 1 by itself, and then tjn plus our diffusivity delta t over delta x, tj plus 1 minus 2 tj plus tj minus 1 over delta x. So we now have the equation to solve for our Tn or Tj, whatever our Tj might be, and find its end temperature after it reaches a steady state. And we can now use this in our Python, which we'll do next, and we'll run through a mock sample. Just one quick thing I forgot to add. We want n to be our superscript up here for our Tn's. Just to avoid confusion, we want to make sure that this is our temperatures from our beginning state and not our end state. So that's just something to note. Okay, we're going to be starting on the Python now, which is going to be part B, or part 2 of part A and part 2, and we're going to simulate the time-dependent response of a uniform bar initially at 20 degrees Celsius. After it ends, are raised then maintained at 50 and 80 degrees respectively. And we're going to divide this bar up into 100 sections and show the simulated results for an R at 0.499 and an R at 0.503. And I forgot to mention, this R value is going to be our diffusivity times our delta temperature over our delta x squared from the last part of this video. It's just going to be that part, and we're just going to make it into a variable R. So moving on, let's go ahead and set our known constraints here. So we'll have our diffusivity equal to 1. We'll have dt equal to 0.5. We'll have that's dx. So we'll have dx equal to, so I'll have our dx equal to 0.5, and we'll have dt equal to 0.1. And then, like we said, we want the number of dividends in our var to equal 100. And then we can go ahead and solve for our R value, which is going to be R is equal to our alpha times our dt and then this is going to be divided by our delta x squared, dx squared. So there's our R value. So now we can move on and we can set up our array for our bar. So we're going to do T for our temperature array is going to be np dot full, and it's going to be, we want it to have the number of dividends we set, which is going to be 100, and we want each one to have a value of 20. So if we go ahead and see T here, we see that we have a value of 20 for each one. But as we said before, get rid of this real quick. So as we said before, we want 50 on one side, and we want 80 on the other side. And we also said in the previous part that we have temperatures on each side, and they're both going to propagate into that bar that we have. So we need to set that. So we're going to have T is equal to or T0, because our index is going to start at 0. So the first number in our array, the index for Python is going to be 0, and we're going to set that equal to 50. And then how it works now is for the last one in there, it's going to be -1. So we're going to set T -1 equal to 80. And now if we do T, shift enter, we have 50 at the start and we have 80 at the end, which is exactly what we wanted. Okay, so now we can go ahead and set up our calculation that we used for our that we set up with using our energy balance. So we'll go ahead and use that and use it to calculate our new T's in our steady state. So we're gonna have T, and then we're gonna have, okay, so we're gonna do a slice here. We're gonna have it from 1 to -1, which is going to grab all the values from 1 before the beginning index and 1 before the end. So when we do this, it should just all be 20s, because we want the 1 value and it's going to end right before the last value. So we leave out our 50 and 80 values right here, which is what we want, because that's what's going to be changing in our gradient. So we can go ahead and have, we want this because this is numbers that we're going to be changing. And then we have, in our first part, we have TJN. So it's going to be the same thing again, because we want all those numbers in the middle, but we want their original temperatures from the starting time. So T1 to -1, and then plus our R, and then that's going to be times. So we have TNJ plus 1. So in order to do this, we want it to be colon -2. So what this is going to do is it's going to grab all the values except for the last 2 numbers. So based off our diagram from before, this is what we want, because it's TJ plus 1. We don't want the 80, and we don't want that first 20, or the last 20 on that side, on the right side of the array. So, and then we're going to add our TN again. So it's going to just be 2 times our original slice from T1 to -1. And then we're going to be adding, and this time we want the other side. We have TJ minus 1 now, so we want everything besides the first 2 on the other side. So T2, T. Okay. So now we have this array, but the problem is that this isn't really going to set us up for a steady state. It's just going to give us that first time difference that we have of 0.1. So in order to kind of push this forward into time, we're going to have to do a for loop. So we're going to do for I in range, and we'll just start with 100 right now. Okay, so that'll run our equation 100 times, pushing it forward and farther into time. But in order to do this, we need to store value somewhere, because we don't want to put it in to our original array. So we're gonna make a new one, and of our temperature profile. So let's do T_profile. and this is going to be equal. We're just going to make a copy of our original array of our 80s and our 50s, 20s, and 80. So we'll go ahead and do that. So we'll do T. I guess we need to brackets because we're making an array. So we're going to do T copy dot copy, and then I don't know where it came from. Okay. So we'll put that up there, and then we want to append to this every time we run this. So we're going to do T underscore our profile, and we're going to want to do dot append, and then of our T dot copy. Okay. So shift enter on that. File. So the profile is not defined. Oh, I didn't probably run this. There we go. Okay. Okay. So on to the next part. Okay, so the next thing that we want to do is we want to start making our graphs for this for our profile. So we'll do fig equals make subplots. And then in order to do this, we're going to need to create a for loop to kind of graph each one of these iterations that we see. So we're going to do for k in t underscore pro, and then that, and then we're going to have fig dot add underscore scatter, and we're going to want our x to equal our np dot arrange of our n, which is basically just going to give us an arrangement of from 0 to 100. So it's like 0, 1, 2, 3, 4, 5, all the way up to 100 to give us our positions on our x graph, or our x axis. So we'll do that, and then our y is going to equal our k. So what this does up here, so we can fix this. So what this does up here is that we can do start and stop, or iteration, or start end, and then every iteration. So we want it to start at the beginning, end at the beginning, and then we can do something like 10. So and then k will pull out values for every 10 iterations from before, and it'll kind of like minimize how much we see. So we'll do that, and then we'll do fig dot show, shift enter. Okay, realized two things I did wrong here. One, arrange does not have two R's. And these should be minuses over here, not plus, otherwise I'm gonna end up with a giant number. So we'll see if this works. Let me go back and look at it. Yeah, okay. This should be a plus, not a minus either. Okay. Still a huge number. Okay, well, I didn't run something at the top, so I went ahead and ran everything and fixed it. So as you can see here, we have our different iterations here that we have, and it's not quite at steady state through 100 runs. We can also, like I said, limit this down. Like if we want to see like every 10, we can look at that and it'll limit us down, and it'll show us every 10 of these iterations right here. So we can go ahead and expand this out and and just see. So it's a lot, but let's do 100 maybe. So, but after 10,000 iterations here, pushing forward and farther into time, we can see that it does begin to level out up here and reach a steady state, obviously. So the next thing the homework asks us to do is to change our value from 0.499 to 0.503. So we'll try that. 0.499, shift enter. We see it reached a steady state here. Nothing really changed too much. And then do 0.503. Next one, ask. And you see that we have an oscillating kind of result here, where it drops down into negatives and it goes into the 47th power of degrees. So obviously something went wrong here in between 0.4, like the threshold of around 0.500, and we'll go over that in the next part. Okay, so in this part we'll be going over why that 0.5 or that threshold of 0.5 cannot be passed using the von Neumann stability analysis. So we're going to have our partial derivative of our t over our partial derivative of our time is equal to our diffusivity and our partial derivative, or our second partial derivative of our temperature over our second partial derivative of our x. So we can say that t is going to be equal to e to the negative diffusivity k squared and then time, then e to the I, k, and x. So these numbers seem pretty random, and values seem pretty random, but the best way to do this is by going on each side of the equation and kind of proving that they equal each other, and therefore proving that valid. So you can start with our dt over t equals, and then using the how e to the ax equals a e to the ax, we know that we can therefore push it, use it here in order for our use. So we have e, and we're taking the derivative with respect to time, so that's only in one e right here. So we're going to have our constants, which is the diffusivity, and our k squared, e to the negative our diffusivity k squared t, and then this doesn't even get messed with because I, k, and x. Okay, so but we can see here that this is still t, like this is still equal to t right here. So we can go ahead and simplify that down and say that our negative diffusivity k squared is equal to t, or times t. Okay, so we can move on to the our next partial derivative. So we need to take this derivative twice. So we have our partial derivative t over our partial derivative of x is equal to e. There's no x in this one, so it just stays as is, k squared t, and then this one goes to I k e to the I k x. Okay, and you can see here that this I k is just constant, or you can move this I k out, and this is still going to be t right here. So it's just going to be equal to I, k, and t. And the second derivative of this is just going to be our I, k, and t squared. Because we're just basically doing the same thing we did before, but our I, k is still there and our t is still there. So let's do that, and we get I squared k squared t squared. Okay, and then we can move on and simplify this down farther. Like, oh wait, this t should not be squared. That just stays as t. But so I squared I is just equal to the square root of -1, but since it's squared, square that, and it just becomes I is equal to -1. So this can be simplified even farther down into -k squared t. So we can plug this back in up there for each of our solutions for each side, and we can get negative our diffusivity k squared t, and then we have our solution for our second derivative here, which is just -k squared t, and then we still have our diffusivity right here, so we include that, and you can see here that these are equal to together, proving that our t here is indeed a solution to our equation. So then we can then take it back and plug it into here, taking our well, we can say that our TJN here, and then we can take it out and use that as a substitution there. Okay, so like I was saying, we can go ahead and add our TJN into that equation. So we have T, N, and J, and we can add it into our proven solution right here of our T. So it'd be TJN is E to the negative diffusivity K squared, and then we have our N change in T. And then we have our other one, so E, and then we have our I, K, N change in X. So that's our TJN, and then so now we have to do it for our TN J plus 1 and TN J minus 1. So we have T J plus 1 N is equal to E diffusivity, this should be J, not N. And then K squared N change in T, E, I, K, J plus 1, and the change in X. So we can go ahead and distribute this out, and we'll get E equals squared and change in T, E to the I, K, IK J, delta X, and then plus I, K, J, or IK delta X. So I, K, delta X. Okay, so right here we can see that this is equal to TJ plus 1 and TN J plus 1 right here. Okay, so we can then substitute that in, and this will equal TN J plus 1 E to the I K delta X. And then we can go ahead and do the same thing for T and J plus or J minus 1. And that will just be a negative right there. So it'll just be T and J minus 1 E to the negative I K delta X. Okay, so now that we have our TJN, TJ plus 1, TN, TJ plus 1, and TN J minus 1, we can then plug it into this equation right here and go farther with it and kind of round this whole thing up. So let's go ahead and plug in these values and pull out our TJN out of our energy balance. So let's go ahead and do that. So we have TJN plus 1 is equal to TJN plus r. It's going to be r plus 1, and then this is going to be multiplied by our values up here. So the first one we have tj plus 1, tnj plus 1, so we can go ahead and plug that in. So it's going to be e. So we pulled out the t and j plus, or this should not be tn. I'll show you. This should be our t and j for both of these. Okay, so these are our t and j's. So yeah, we pulled these out, so we're just left with these exponentials right here. So we have the first exponential is tj plus 1, and so we have the first exponential here, which is I, k, x, and then we have our minus 2, and then we pull out the t and j, and then we have plus our or it's going to be, yeah, plus e to the negative I k delta x. Okay, so then we can use Euler's identity, which is e to the ix is equal to cosine x plus I sine x. And so we can use that, we can apply this up here, and we can be left with equals, well, first, so actually, yeah, we'll go ahead and do this. So t, j, n plus 1 is equal to t, j, n plus r plus 1, and then apply this, which is just going to be cosine k delta x plus, well, we won't, yeah, we can go ahead and do it this way. It's fine. And then plus, or minus 2, or yeah, hold on, plus I sine x, and then minus 2, and then plus our cosine delta x, and then the k, and then it's going to be a minus, so we have a minus I up here, so it's just going to be minus, and then sine delta x and k. And you can see here that these will cancel, and you'll be left with t, j, n plus 1 is equal to t and j plus r plus 1 times cosine, it's going to be 2 cosine delta x k, and then minus 2. Okay, so you know cosine, we want to keep it in the range of 1 and negative 1 for our amplitude, otherwise it doesn't really work. So we want to set this value right here in the constraints of 1 and negative 1. So we want it to be 1 equal to r plus 1, 2 cosine k, and minus 2 negative 1. Okay, so we have r plus 1, 2 cosine minus 2. So the first thing that we can do is go ahead and subtract everything by our minus 1 right here. So we have 0, r plus, or r, 2 cosine k minus 2, and it's going to be negative 2. Okay, and then, oh wait, I mix these two up. We want it to be greater than negative 1 and less than 1, so Negative 1 should be here, and then subtract 2 over, this should be, or negative 2 should be right here, and then this should be 0 and 0. Okay, and then like we were saying, the most extreme values can be negative 1 or 1. So we can go ahead and set this cosine equal to cosine pi, which is going to be our negative 1 value. Cosine of pi is going to be equal to negative 1. So we can go ahead and do negative 2 r, and then we have negative 2 minus 2 plus minus, and then 0. So this is going to be 4 right here, and then we're going to divide each side by 4, and we're going to get that negative 2 over 4, which is just going to be 0.5 r, and then this is just going to be 0. So we can see that r needs to be well, we divide by negative, so the sign switch too. So we can see that r is going to be less than 0.5 and greater than 0. So it's got to stay in between 0 and 0.5, and that's exactly why our Python code ran into such an error and why it was so volatile, and that's why, because our r was greater than 0.5, and that is not allowed according to our cosine amplitude. So that's it for the homework. I just realized you couldn't see the side right here, but there's that.